I would like to introduce Dave Adams, who will be speaking tonight about a subject that's important to all of us, the Snake River Aquifer and its boundaries, or what the famous geologist David Love called the soup bowl. Soup bowl. Dave Adams started skiing in Jackson in 1968 and then went to work for the Snake River Ranch in 1971. He moved to Jackson full-time in 1976. And he was actually lured into studying geology by David Love in the late 1980s. Dave received his MS in geology from Montana State in 1997. His thesis was on the igneous petrology and geochemistry in southern Jackson Hole. And then he went on to receive a PhD in geology/geophysics from the University of Oregon in 2009 with a dissertation on seismic tomography of the Yellowstone hotspot. He has been on the board of supervisors of the Teton Conservation District since 2002, and since 2011, he has been president of a family mineral management firm in Minnesota, primarily engaged in the mining of iron ore. So with that, Dave?
Great. I am going to assume that with all these wires, everybody can hear me. Thank you all for coming. This is great to see such interest in where our drinking water comes from. 30, 40 years ago, when a lot of this research was being done, the burning issues in the valley were landscaping berms and plutonium-free powder. So I think we've finally got our heads around to the real issues now. This talk is going to be kind of a smorgasbord. We'll jump around from various projects, research projects to other ones. So don't wait till the end to ask any questions. You can interrupt anytime. Don't worry about derailing my train of thought if I ever have one. It left the station a long time ago. So let's see, where was that? Okay. Soup bowl. As Cynthia said, Dave Love was the person who coined it, the soup bowl. And it's an unusual combination of geologic events and structures. You got a very nice half graben that filled with about 3,000 feet of ice, scoured out a nice trough, mostly on this side, filled it with highly permeable quartzite cobbles, and then probably most importantly, down here, there's bedrock sill that actually forms the southern lip of the soup bowl. So we're going to be discussing today kind of the work that have helped define sort of what the shape and depth of the soup bowl is. We'll look at how the material in the soup bowl changes horizontally, vertically. And then we'll examine not only how the groundwater interacts with surface water, but also the fact that what we think of as the aquifer is actually kind of unusual when you look at the valley as a whole. That worked. Okay.
Okay.
Yeah. Arrow keys. Huh. What is going on? Yeah, I guess we made it pretty far. Anyway. I just picked on the screen. There we go.
Oh, thank you.
Now, in the late 60s, USGS sent some of their gee whiz kids, which is what Dave Love called geophysicists. And they did a refraction study across Teton Park. This is the first time we'd really looked at, the valley floor and what was underneath it. I mean, because it's a soup bowl, you don't have to drill very far to get water. And also we're particularly unblessed with oil and gas resources. So nobody had bothered to really do much of the way of deep well drilling. But the problem with this is, as you'll notice, they were just looking at these various contacts, and they kind of had Precambrian rocks, Paleozoic, Lower Mesozoic, and then Cenozoic and everything else. So this doesn't tell us very much about the aquifer itself, the porous recent sediments. Now just click on the screen.
Swipe.
Okay, there we go. Okay. They also did some gravity studies, and this highlighted the fact that you have kind of a gravity high here, indicating you've got some denser rocks at depth, and gravity low in this area, and then a real step up to higher, more dense rocks right where the Warm Spring Fault is. Gravity studies are not particularly unique. In other words, you can put 500 feet of lime jello in here and make it work. What we really needed was some way to constrain what the depth was, what the shape was. And this was particularly so when people started talking about doing injection wells, because they would design these beautifully engineered plants, and then they inject it into something that they had no idea what it was. And Dave Love said, we got to figure out some way to study this. So we kind of came up with an idea of some seismic lines going this way and that way, and priced it out at about $500,000 in 1990. And we weren't going to raise that. And it was really funny, most of the residents of Teton County don't like explosions unless it means they get to go ski on it afterwards. So we settled for a audio-magnetotelluric study, which takes advantage. It's a lot cheaper, for one thing. We raised 10,000. The Conservation District matched that, and the USGS matched that and sent a crew up to do this. And what we're taking advantage of is the fact that lightning strikes all over the world kind of travel in the ionosphere as far as electrical impulses, and they induce magnetic and electrical impulses in the earth, and you can read those by laying out what they're doing. Here's Mike Centerfit. He's laying out a nice dipole, an L-shaped dipole, and that's going to measure the electrical fields. And then right at the center is his coil to measure the magnetic fields. And what you get is that the lower the frequency, the deeper it penetrates in the earth. So you can get kind of, by checking all the various frequencies, you can get a kind of a resistivity by depth. The aquifer is a high resistivity. The bedrock is a low resistivity. But you can see it gets kind of dicey as to where you're going to draw the line. Plus, one of the problems we had here is that the Madison limestone is heavily karstified in most of the Rocky Mountains. And when it is, it looks just like unconsolidated sediments filled with water. So we were trying to find places where you had just enough of the Amsden shale on top of it, so you get a real good contrast, resistivity contrast. But they struggled through it, and they ran their kriging and their geostatistics and came up with this map, which they published in '98. And it looks pretty good. It's got a nice deep hole right near Wilson. There's one problem. You see the problem here? The aquifer appears to go right through the buttes and is going merrily under the Tetons without stopping. And I thought, oh, come on, we can do better than that. And they said, no, I got to publish what I find. And I thought, well, you got all this free data because you've got all this bedrock exposures all over the place. You can put those in. Those are better than the stuff you measured. And when you do that and rerun your statistics, you come up with something like this. And this shows, it's not quite so deep, but you've got some deeper areas. These are more like 300 or 400 feet deep in this area along Wilson. You'll notice in certain areas where there's not too much information, the model goes to extremes, kind of like American politics. And but one thing of real interest is this structure here, which is about three or 400 feet, and it goes kind of diagonally across there. And it looks suspiciously like a fault trace. Remember, down in this area, we're changing from Teton fault over the Hoback normal fault. So you're going to get some transfer structures in between. At any rate, that seems to be what we're looking at. Aquifer gets very shallow down here toward Melody Ranch. And up here, we really don't have enough data to say anything. But it seems like a lot of the scouring was done right in this area. Now, the question is, okay, we've got a vague idea of how deep it is. But the question is it the same in all directions? Is it homogeneous? I mean, is our soup just nothing but peas? Or do we have some carrots in there? Does it change as you go to the different areas? And one of the clues that we were getting was when the Ski Corp was drilling one of their new snowmaking wells, which are pretty high capacity wells. They really, pump a lot of material. And I think it was Nelson Engineering was doing the testing, the drawdown testing of it. And so they're up here by the village out in the field, and they had a shallow monitoring well, just about 20 feet away from the snowmaking well. It went down about 15 feet. And then out about 200 or 300 feet, they had a 50-foot monitoring well. Well, they cranked that baby up, and the level in the 50-foot well just sank. It just plummeted. It was gone. Nothing happened in the shallow well. That suggested you've got something between those two wells, say around 30, 40, 50 feet, that is operating as an aquitard. It's not, you've got something that is preventing water from moving vertically without restraint. So I was thinking, well, how are we going to get around to studying this? And the only way we can really do that is by using the water wells that Jack Weber and his people have been drilling here for eons. Unfortunately, if you look at a well log of a water well, and I've looked at more than I need to, it's usually sandy gravel, gravelly sand, sandy gravel, and then that's it. But fortunately, they all collect grab samples, usually every 5-10 feet, and keep them for a period of time. And so I asked, Jack if he had any sitting around. I asked him to hang on to them, and he said, "Yeah, I got them." And he says, "But you have to get them out of my shop because they're taking up space." So we got a Ewing, the Ewing's well right up here. We had Teton Acres down in near Coyote Loop, Stearns Well down in Wilson, and several down in Melody Ranch, and then about a 280-foot exploratory well from the city. So that's what I had to work with. We also be talking about, these are the shooting iron outcrops that I also ran the tests on. Now, the problem is that when Mudrat would be out there taking a sample, you pick it up in a bucket, you dump it out, you take your hand, you scoop a bunch out and put it in a Ziploc bag. So you're not going to be able to do a particle size distribution study on it. You have to find something that is unaffected by their collection method. And so I thought, well, let's see what the clay size fraction is. Clay size in this case means 1 micron or less. So you take these things, you sieve them down, you suspend them, you centrifuge it down, get it down to 1 micron, and then you do a oriented mount on, don't want to make it bigger. I want to make it go away. Okay. There we go. And then we do X-ray diffraction on it. X-ray diffraction is kind of an interesting thing. It's kind of like when you're driving by a cornfield or an orchard and you look and you see nothing but trees. It's just no particular organization. Then as you pass one particular point, all of a sudden everything lines up. Well, that's what X-ray diffraction is. You're taking an X-ray beam, running it through an angle over your sample. And these are the characteristic peaks for various minerals. In this case, the bottom you have, these are illites, which are kind of like mica-like clays. Here's what smectites are. Those are your swelling clays that make driving around rural Wyoming so much fun. And here's kaolinite. Then you also have some more smectite, illite, quartz peak. There's another kaolinite peak, quartz peak, and a calcite. And what we're looking for is any kind of change in these things as we go down through these samples. Now, this is the Stearns well in right behind Hungry Jack's. This is 25 to 30 feet. This is kind of typical of what you see in most of the, outwash there. But this is from, I think, 30 to 35 feet. And you'll notice that the quartz goes through the roof. Plus, you also start getting a certain amount of calcite. Now, it's really interesting. Quartz, when it erodes from a rock and gets tumbled down the streams, it gets broken up, gets smaller and smaller, keeps on bouncing along the bottom of the stream bed, gets to a certain size, gets to about 50 to 100 microns, and all of a sudden it goes into suspension, and you can't break it down anymore. But there is one thing that does make clay size quartz particles, and that's glaciers. And that usually gets settled out in glacial lakes as glacial flour. And if those dry up and the wind gets it, then it gets distributed all over the countryside as a loess. That's an umlaut. Everybody say after me, loess. There we go. So this is what we see here. Now, when I looked at Mudrat's log, and it was gravelly sand, sandy gravel all the way down. But when you actually got to this sample, there was no gravel in it. But it was so thin that when he was averaging it out, he didn't ignore it. It was nothing but silt. So it was pure glacial silt. So that's a good candidate for your aquitard. Now, here's the Stearns well, where you see, here's that first sample. Here's the one with all the quartz in it. The red is calcite. There's a tendency in subaerial deposits of loess. When the rainwater comes down, remember, rainwater is a dilute carbonic acid. So as it goes down through the loess, it's going to react and it'll end up precipitating usually lower parts of the loess as a calcite. So that's also another sign that you've got a loess there. Now, it's not there everywhere. The Ewing well you don't see it. Teton Acres, not really. Don't really see much of anything. And you can imagine that that's because, if you've got wind deposited material, if it falls right into the river, it's not going to stay there. Or if it falls someplace and the river shifts and erases it, you don't see it. But in this case, it probably fell into a slight little backwater where it could accumulate as a pretty decent thickness. The interesting thing about that is in places where you do see it, it seems to be at that 35-foot level, which indicates if it were all a lake, then you would expect that it would get deeper as you went north of the valley. It was all at the same elevation. But it seems to be at the same level below the surface, which indicates that another thing that indicates is probably a loess. However, when you get down to the Melody Ranch, you see something entirely different. We're just chock full of, calcite and lots of quartz, and this is the area where when the Bull Lake glaciers melted back, the terminal moraine would have impounded a fairly large lake. And so it reflects all the glacial flour that was settling out of the lake. Now, I couldn't find any of the permits for any of these, so I don't know exactly where they were, but it looks like if you were going to put these in relation, this is uppermost, this is lowermost, and this kind of splits the difference between the two. I got a little, it's trying to help me, isn't it? Try this. Oh, there we go. This is a cartoon I did for a presentation a while ago, and you can see I don't have a career with Disney. Here we are. This is Bull Lake Glacier, full glaciation. This is about Teton Village. This is Munger Mountain, and you can see all the ice that's sitting on top of the pre-glacial sediments. And here's the terminal moraine, and here's some outwash from there. And later, as the ice retreats to a kind of a still stand that's sort of by the village, this lays down not only this greenish ground moraine here, but it has outwash coming off of the toe of the glacier. And here's that glacial lake down there, Melody Ranch. It's being impounded by the terminal moraine, which isn't going to last forever. And eventually those things do break, the lake drains, and you have a tremendous amount of exposed glacial flour. The wind comes up, it spreads that layer. This is our little aquitard layer. And it also puts a bunch all over the rest of the countryside, especially up on the highlands around there. So you can imagine this is, say the area above Swinging Bridge up in Squaw Creek. So you got a list there. As time goes by, you have these are early Wisconsin, but eventually you do get the Pinedale glaciation, which doesn't have ice down this far, but also puts down a glacial outwash, about 30 feet of it on top of our little aquitard. And it also probably has additional list layers here. And you can see where the various wells are. Here's the Stearns well, and here's the Melody Ranch, which is drilling mostly into these lake sediments. And here's this city exploration well, which goes down all the way into the pre-glacial Pliocene sediments. Now, this is some work that Ken Pierce did right up above Swinging Bridge. He was studying, he found a package of about 8 lisses, and that covered is about 9 meters and covers 154,000 years, Bull Lake all the way to present. And he was using, to date this, he was using thermoluminescence, which is another neat little toy that you could use to measure the last time a sediment saw daylight. He used that and a bunch of cosmogenic stuff and also soil formation time. So this is actually a pretty good history of list production from the Bull Lake on. And I would say that the list that we're seeing in the Stearns well is probably this one. And you can see it's a pretty good thick unit. The important thing to keep in mind about these lisses and stuff like that is you probably don't want a lot of this material in the aquifer where you're trying to drill. It's not very transmissive. Okay, now let's look at what was the pre-glacial sediments. These are the shooting iron formation. These are dated by paleontologically, land snails, I think some mollusks. And here's the exposure down at the type section. This, down in this area, right where the bend in South Park Loop Road is, this is looking west at it. It's got a little bit of glacial material on top, and then here's the top of the shooting iron, and it's dipping about 12 degrees to the north. And here's as you're going down, around this corner into Shooting Iron Ranch, and you can see some of the lithologies that we have here. Some fine grain units, not a whole lot of what you call real good, clean conglomerates. Now, this is the other end of the Shooting Iron Formation. This is up in the Elk Refuge, and you're up in the orient myself. Yeah, you're up here. This is kind of where the old ditch that used to take off here, they let it kind of go kind of willy-nilly through the sediments, made a very large canyon, which is great for me. I mean, great exposures. But they eventually put a pipeline in it. Now, these are sort of mapped as parts of the same unit, but they're quite a bit different when you look at them under a microscope. Here you'll find a lot of things like pyroxenes and hornblends and a lot of glass shards. What you would expect if you're eroding out of the Tiwanaut into this area. And down here, it's all zircons, apatites, and no shards. So these might be two different facies of either side of the same lake, and they're just getting fed different materials, or they could be quite a bit separately, but they're there at the same time, and both of them are fine grained, so they're not particularly what you really want to have as far as a good producing aquifer. Okay, when we take a look at those two as far as the quartz and the calcite, shooting iron, you can see this is this little glacial member way on top. You get into shooting iron from here on down. Not much to speak of as far as quartz. Elk Refuge got lots of calcite and a certain amount of quartz. And then you had about this level, you have pumice. Now here's the city exploration well. Up above, you don't see much, but then right down here, you start seeing pretty much this kind of signal. And there you have pumice at about 210 feet. So I'm pretty confident saying that we're seeing this particular deposit reflected down in the city exploration well, which is right near Ely Springs. And, the city explored it, but, you get down into this kind of material, fairly fine grained, tight, it's not going to produce enough for Jackson. So, they went elsewhere. Dave Love, he loved it. Every 25 years, the town of Jackson would come to him and say, Dave, where should we drill for water? And he'd tell him, well, don't drill in the town of Jackson. And they say, okay. And then they look around, well, we don't own any land anywhere else. So they drill in the town of Jackson and not find water. Okay, let's look at another little mystery area that came to light recently. Those are one of our favorite slides, literally. And this, of course, is, I call it the Budge Slide. Yeah, the Budge Drive Slide, Walgreens, whatever. Here's the outline of material that was moving. These are all the cores that were drilled. And they were nice enough to let John Hemiger and me poke around. Do you know if they're still over there? They're still, or did they?
Said they keep them, but
I think they might have gotten trashed. Anyway, yeah, we had a chance to look at it, and it's an amazing thing. I was in this area before the slide, looking at the work that the geotech was doing just for the foundations of the Walgreens. And it was interesting because he could study right up to the boundary line, which was the base of an unreclaimed quarry face. And he was not allowed to look at anything on the other side of it. So if you're wondering whether geology matters to some of the forces that be in our government, that's a good answer. Okay, here's a cross section created by Professor Habiger, and you'll notice I'm using your alternative, not the one I preferred. But
Your interpretation, Dave.
yep, they're all just stories. We're just making it up. But you can see what the basic story of this is. At some point in the past, probably right at the end of Bull Lake, these large chunks of basaltic andesite, about 7 million year old rock, which were up at the top of the butte, came down to the bottom very suddenly, and kind of landed in a bunch of fluvial and also lacustrine, very fine grained material. Some of it's got some cobbles, but this is kind of the interesting part. And here you see what it was trying to do. Before they really started excavating, it was sitting there quite comfortably. And then gradually over the years, we took away all the things that were keeping this book from sliding out. And they finally got down and took the last little bit out, and it wanted to pivot. So it's pivoting and it's pushing all this stuff up and out. And here they actually were very nice enough to spray paint their actual glide plane of the fault, for the slide. And what it was trying to do is it's trying to tow out, and probably if they let it go, it probably would have splayed out even further. Here's Broadway in the background. But the interesting thing is I hadn't seen any of this anywhere else in any of my well samples. You know, this is unusual. And also what was really unusual about it, it was right up tight against the butte. You know, and normally what you'd expect against the butte would just be all this slope wash, alluvium falling down, not a lake. So it's quite possible that the history of the town of East, or the East Jackson area, was that perhaps for a long period of time, the Flat Creek actually stayed right tight to the butte and maybe even flowed out by Cuddies. And then at some point or another, that was blocked off. You had a lake develop. But you had to have that incising of the butte in order to allow the lake to get that close to it. So it's quite possible that there's a lot more of this underlying everything out here. Once again, nobody really needed to drill for water in the town of Jackson, or drill very deep. And the only people that were doing it was people who were chasing benzene plumes. And all that evidence was burned, I think. So. Anyway, I went and sent a bunch of the samples up to Montana State. Dave Moak had a bunch of students. He was teaching them how to do XRD, the X-ray diffraction. And they ran it, but somebody had taken the centrifuge, and I think they were making smoothies with it or something like that. So they had to use a slightly different technique. I think it's pretty good. At any rate, we didn't really see a tremendous amount of silica. This is a loess that was identified as loess. It's right up high in the section. And this was down near where the original, where the parking lot was going to be behind the Walgreens, which was totally different from all this. We didn't see any of the dark stuff in that. It was all light colored siltstone with some coal in it. So there's a tremendous amount of variation along here. But also at this level and some other places, we had lots of critters. So if I weren't so lazy, I would just go and find a critter person who could tell me the age of these little bivalves. And we would probably be able to say pretty confidently whether it's, this is Pleistocene or more related to the shooting iron formation. So if anybody in here is a critter person, paleontologist, or knows one, we have these, I have these samples. The town probably threw away the rest of them, but we have these. So anybody who wants to take a stab at that, that'd be great. So now I'd like to do a little bit of a digression. Last month, John Bird brought up an observation that Dave Love had made, that there was shooting iron at 10,000 feet in the Grovans. Well, Dave, knew I was doing all this work on the shooting iron. He said, well, Dave, why don't you just scamper up there and grab some and run it? And so I did. Here, what we're looking at is we're looking west up to the head of Granite Creek. Here's Dinwiddie, so this ridge top made out of this alleged shooting iron is sitting on an unconformity on the Dinwiddie. Here is standing on top of the ridge, and we're looking to the southeast up the ridge, and you can see in the distance, this is the steeply dipping northeast flank of the Flat Creek syncline, and there's the all steeply dipping Madison limestone goes up here and then trots on down Flat Creek toward Kelly. So anyway, when I do run them, here's something from the shooting iron type section down in South Park. And you see you've got all the typical, characters, all the various peaks. And then you have this, which doesn't look like anything else that we've seen. You have no illite, absolutely none. Essentially, almost no kaolinite, very little quartz, but really prominent swelling clays. And what this looks like is a bentonite. So, and you can see this a little bit more clearly if I plot a ternary diagram. These things are great. I love ternary diagrams. And you can see here's the Granite Creek Divide samples, mostly swelling clays. And they're much more than either the shooting iron type section or the Boyles Ditch elk refuge section. And you notice these things obviously, look quite a bit, dissimilar in this case. Bottom line, I would prefer not to hear anybody talk about shooting iron at 10,000 feet anymore. It sits in a place that it sits right in the bottom of the syncline. These synclines are really asymmetrical. They just go like this, like that big Z folds. And here they have mapped not only shooting iron here, here's that ridge, but they have shooting iron out on this ridge, shooting iron here, and they also mark some Tiwanaut. But what's really interesting about all these things is they're all sitting in the syncline, just like that. And what that means to me is that these are probably synorogenic. In other words, as it was being folded, they were being shed off the corner of the fold into the low area next to it. And there also, when you look at a microscope, if you look from bottom to top, what you see is a really nice, what they call an unroofing section. In other words, the bottom ones have a lot of apatite. Then you have a bunch of rounded quartz, and then you have a bunch of Madison limestones, which is what you'd expect if you're wearing down through phosphoria, down into intensely, down into Madison limestone. So that's my story, but I got to get up there and collect the rest of these things and work them up a little bit. But if you're going to have this mono up 10,000 feet, that would be about over 3,000 feet of uplift in 2 million years with no sign of any surface ruptures. You better have pretty good evidence to show that these are shooting iron. And I don't think they are. I think they're probably Miocene. Anyway, I had to get that off my chest. Oops. Okay, the relationship of the groundwater to streams. this has been a big deal, especially as we're looking at, how are pollutants entering Fish Creek. This is from a study Nelson Engineering did in '92. This is groundwater contours in end of June, so high water. And you can see that these contours are pretty much perpendicular to the snake. So it's this water is flowing the same direction. The snake is kind of controlling it. In other words, the water is moving out of the snake and then flowing in this direction. But as you get further down, you'll notice that there are some perturbations, and down in this area, it's angling a little bit more away from the snake and toward Fish Creek. We know it's a soup bowl, and we know that the water that's in it, if it's moving, has got to leave it at some point. And we're fairly certain that it doesn't all leave it right down at the South Park Bridge where it hits bedrock. So we started doing some studies to see, well, exactly how much of it is coming up into Fish Creek and where. And these are two studies that Conservation District did with the USGS to try and measure this. This one is essentially, you just do a budget. You carefully measure every little stream that's flowing in, every irrigation ditch that's going out, how much water is in, and you get a budget. And you can see whether you've got a gaining stream, whether it's coming up from the groundwater, or a losing stream where it's going out. And this one was even neater because we were using heat as a tracer. And this is an interesting technique. The water in the surface water is going to react to the diurnal cycle. It warms up during the daytime, cools off at night. Groundwater doesn't do that. So what you do is you put in your sensors and see whether that diurnal signal is penetrating down into the ground, which would suggest that you've got a losing stream there, or whether you're seeing the normal diurnal cycle in the stream getting damped down because you're getting mostly groundwater at the same temperature. And so when we do that, actually both of these techniques, the budget and everything, showed that, yeah, there is a fair amount of gaining from the groundwater. It was done pretty much at three areas. Teton Village, it's dry. That reach is dry most of the year. But when it isn't dry, when it's flowing, it's gaining a tremendous amount from the groundwater. The next one, Reeser's Bridge, it is a losing stream during the winter time, and then it's a gaining stream for this is high water, and in the winter time it's a losing stream. And then the Wilson, it's just a slight gaining stream all year long. And this is important to know because this means anytime you have any kind of connection between stream and groundwater, then you can kind of treat it sort of as one system. But a lot of other areas in the valley, it's not that way. For instance, when we were doing a septic tank monitoring study, which we finished up last year, we picked 4 septic tanks to monitor, and we wanted new ones. We wanted high groundwater, that we could get samples from the groundwater all year long. Well, that was fine for our 3 sites over here, but the site that we had that was right near Boyles Hill, come the fall, the groundwater just dropped out completely. And this property is right next to Spring Creek, which was flowing merrily along. And this is quite common. In fact, what you'll see in Flat Creek as it goes through town, anybody who's gotten into Flat Creek and trying to do anything, realize that the bottom of Flat Creek is as hard as the back of somebody's head. And also, when you look at the water level, say in the thaw wells that are along it, which are right next to the creek, and they're probably, the wellheads maybe only 6-8 feet higher. The levels are down 18 feet, 35 feet. So these are perched streams that are not contributing, any kind of recharge to the water table. And that's important, especially for some place like Spring Gulch. If that's true, then the bulk of the groundwater in Spring Gulch is not coming from Spring Creek. It's coming from flood irrigation. And as flood irrigation turns into real estate, all of a sudden you're not getting the recharge you thought. And so a lot of these areas down in here may find their water level starting to drop. So a lot of the fens and springs that we see around here may start to dry up. But in general, what I'm trying to say is that we tend to think of the aquifer, you know, the soup bowl here. And it's actually kind of unusual because you go over into here, the area by Walton Ranch, that's all just, you know, absolutely fine swamp sediment. Stinks like heck when you dig it up. Yeah, it's fine grain. You're not going to get any water out here. As we said, you know, there may be a little bit of recharge here, not too much. Down in here, you've got a tremendous amount of glacial flour. Makes it really hard to you know, get a well producing without throwing a lot of sediment. Yeah, town of Jackson, you know, you're into lake sediments and everything. Up in this area, you've got the Teton. Everybody wonders what's the Teton doing there. It's essentially just loose ash. How did it stay there when the glaciers came through? Well, the funny thing about impervious things is, you know, you can put a big glacier on it and it'll develop this little film of water right on top of this stuff, and it's like grease. And the glacier will just leave it all alone. But anyway, you're not going to get much of any kind of well development in there. I mean, there are people that do produce wells. So what we have to keep in mind is as we go along, we talk about water sources. This is great. The rest of the area, maybe not so great. And we have to keep that in mind, that we're not talking about just one aquifer. We're talking about a very complex beast. So at that point, I'd love to have some questions. I know you've got some questions. Yeah.
Has the size and volume of the usable aquifer?
Well, the things that go into that is not just the aquifer. You know, do you have something that's really transmissible? I mean, the groundwater flows about, I think we clocked one at 288 feet per day over here. And that's at the surface. We don't know what it's doing down at depth. We have no way of knowing. But obviously you can pump out of here all day long. But any other places, maybe not so much. I think eventually town of Jackson is going to start having some issues. So, and of course you get up into some place like Ditch Creek Fan and stuff like that. You know, in this area, you know, the area near the airport, that doesn't get any recharge of the Snake because the valley's tilting this way. All the flow is going that way. So they're not getting recharge. In fact, so you know, we were doing studies on glycol on the wells. And you can see, I remember one fall, it was almost like as soon as people showed up for Thanksgiving, the water level dropped like 10 feet in one of the monitoring wells. I mean, there's not a lot of recharge in this area. And so it's really hard to say that. It depends on where you are and how much you need it and how fast you need it. I'd say if you could get everything out of here, it would be fine. You could probably handle the whole valley. Yeah.
You know where the town of Jackson water source wells are?
There are a couple of them. Dave, help me out. Mm-hmm. Yeah. Yeah. And none of those are particularly good areas as far as aquifer material. I mean, the area of the elk refuge, that's, you know, a lot of lake sediments in there. That's why you have it, you know, all that grassland there. Yeah, they irrigate it, you know, so that's helpful.
So we do have a question from chat, if we could do that. The construction of the new Jackson State Bank had a lot of trouble with building because their excavation filled with water. Is that the level of town groundwater?
Could be that locally. I'm not familiar with that. The new Jackson State Bank,
Anybody know where that is?
there is no new Jackson State Bank.
Across the street, is the across the street from the old one? Yeah. Across from the, right down by the REI in that area?
Oh, down by REI?
Yeah, I believe that's the one they're talking about. I have a question.
Yeah.
Okay. In your observation, my father and I, someone here, when they were doing that, wall underneath or whatever it was.
Mhm.
And we both said that thing's gonna slide.
Oh, yeah.
Did you feel that way?
I've been looking at that. I thought that at least that I was worried about the integrity of the andesite rock unit. I thought it was gonna fall apart. It was pretty well shattered, but you know, it turns out it was strong enough so that when it started to move, it certainly did. I wasn't sure, people weren't really sure whether that was a fault, it was down faulted, or whether it was an isolated rock unit, which would have made a big difference.
It's one of the things that I was watching them build it. And once they built it, it's kind of like, okay, they've stopped, maybe it's gonna, who knows what it's gonna do. But they kept trying to enlarge the parking and kept cutting back into that bank further and further and further.
Yeah, it was actually, that level wasn't the problem. It was, they dropped the whole site.
Yeah.
You know, from when it was Slim Chance down to that, they dropped it 6 feet. And that's what really got things going. And then it was just a matter of getting a nice wet winter, good melt and grease the skids. So. Yeah,
Actually, we were talking about Dave Nelson. Him and I were working together when the first concrete wall was built on that whole
right.
stretch for Jimmy Anderson.
Hmm.
That was 50+ years ago.
Yeah. Well, most of that toe used to go most of the way out across Broadway. If you look at the old 45 aerials, 1945 aerials. Yeah, and then they said, oh, let's use this. So all that material went into the roadbed for Broadway. Right. Yeah.
These compositions lend themselves to liquefaction.
In certain
So,
areas, yeah.
Let me just repeat the question. The question was, do the composition of some of these deposits lend themselves to liquefaction?
I would say any place you have lake sediments, this whole area in here, that could liquefy. Have you driven by that, where it's all a lake in the springtime? It was called Kissinger Lake on some maps. Yeah, that could liquefy all that area. A lot of this material could liquefy. I'm not sure, the properties of volcanic ash, whether that really liquefies as much as, where you have sand and rounded grains, because everybody's seen liquefaction. You go to the beach and if the sand is wet and you hit it, you can see it all of a sudden it liquefies. But you need some rounded grains.
Seasonal, like a higher risk.
Yeah. Yeah.
Sitting on the questions of groundwater invading the construction site when the Western Carrot was being rebuilt, they expanded the foundation lot and they had to de-water that almost constantly.
Mhm.
to get the concrete.
Yeah.
So just for Zoom, the comment was when they were rebuilding the Rusty Parrot in Jackson, they had to continuously de-water the site because of groundwater coming in.
Yeah.
Downstream, they find evidence for that. 30 to 50 foot off the target.
Well, it was in the exploration well, city exploration well. And then it was in the Stearns well. I thought I saw it in another well, but I went and looked at all my data again. And so to be honest, those are the two. where it showed up pretty strongly. Yeah,
Dave, the injection wells that Teton Village and Teton Pines have now been running for 20 or 30 years. Have you found any like long-term influence on the aquifer?
can I plead the fifth on that?
Let me just repeat the question. So the question was, there are injection wells that have been running for 20 or 30 years in Teton Village and the Pines, and have they been impacting the aquifer?
I think by definition they are. Even though they treat it to a fairly high degree, you're still putting in nitrates at a level that's 3 to 5 times the background. And what's more important for me is that you're putting them in at a deeper level where tree roots, and then there's not going to be any uptake, possible uptake from plants. And so it's quite possible. And we never did any studies of the flow at depth. We could have done that. And we could probably still do it now. At the Pines, they have, I think, 5 injection wells, and they're only running like 3 or so at a time. All you have to do is what's called is a borehole dilution test, where you take a couple, rubber pegs, you isolate a certain level in there, and you put a device down there with a certain amount of salt, and you can measure how fast that salt gets washed out of there. And it would be really nice to know if you're getting the same kind of flow rates at 100 feet that you are at the surface. But I tend to think you're not. So yes, I think that probably they do have a fairly large effect on what's going into Fish Creek.
I missed it. What are they injecting?
They're injecting tertiary treated effluent. So they are down around, I think, the village, they're injecting at 50 feet, and they're running, 2 to 4%, 2 to 4 parts per million nitrate. And
They're injecting sewage water.
they're treated. It's essentially drinkable. But it's more than nitrates than in the background. So it would be nice if we just found some other way to deal with that material. But keep in mind, they were told that they had to do that. That wasn't their choice. They were told by the county commissioners that they had to do that. So as far as I'm concerned, it's the county that needs to clean up their mess. Yeah.
Just looking at the main landscape, there's no evidence any of the moraines gave way to a glacial lake, correct?
Oh, yeah, I think that, the main terminal moraine down here, that clearly gave way. Yeah. It impounded it, and whether it was as sudden as the Kelly flood, probably was. It's all loose material, and so it impounded a lake for a while until the lake got up high enough to start cutting and breaching the far side. So it was probably a catastrophic flood. No, because it wasn't going into a big wide open area where you could have ripple marks. It was going right down a confined canyon.
Is that why there's rounded rocks a little ways down the Snake River from there?
Could be.
I guess it's past the sporting ranch.
Yeah. Well, a lot of that is also the Dog Creek Slide has been occurring on that ridge forever, shedding material into the river.
Just see it above the highway.
Yeah.
Spot that touches around the rock.
Mm. Yeah, that could have been a flood deposit. They've done a lot of work on, trying to, grade terraces back to what they think they belong with. That's not something I've spent a lot of time looking at, but a lot of people have done that. It's kind of well documented. Yeah.
Is the extent of the aquifer affecting the aquifer as a whole at all? Like, are they kind of operating two separate aquifers, or?
It's not
Let
a
me just,
complete
Let me
aquitard.
just repeat the question here. Sorry for Zoom. the question was about the aquitard that we've been talking about, the one about 35 feet. Is it a complete barrier such that you have two aquifers, basically, one above and one below?
It kind of depends on how extensive it is in any one area. As I showed, there are a couple places where it's absent. Can't see it. But in a small area, it would serve, for instance, one of the theories that a lot of people had was the reason we could get by with leach fields was we were getting our water from 60 feet. We're, totally destroying the water up above there. But, and so that made a lot of people kind of concerned when they're saying, okay, well, we're going to inject effluent down at that level. But it's not a perfect aquifer. I think probably in most of the valley, you don't really see it because it's either gotten washed away or wasn't deposited in the first place. Well, great, thank you.
Okay, there were no more questions from Zoom, so I think we can wrap this up. And as a token of our appreciation for doing this talk that we're all very interested in, here is a present from the geologists of Jackson Hole.
Thank you. My wife will be.
No